In this video, we're going to talk about how to use the graph of a function to understand the inverse of a function. So here we have the graph of some function. Let's say it's the function f. All right. So we know how to evaluate the function f by looking at its graph. So for instance, I know that f takes the number 1 and produces the number 2. And I know that because if I take 1 for x, I'm here on the x-axis at position 1, I go up to the graph and over to the y-axis, and that's the value of the function. Because every point on the graph has the form x comma f of x. And so this point's x-coordinate is the value of x, and the y-coordinate is the value of the function. And similarly, if I evaluate the function at 2, when x equals 2, the value of the function is 3. If I evaluate the function at 0, the value of the function is 1, and the value of the function when x is negative 1 is 0. All right, well, how does the inverse function work? Well, remember, the inverse function goes the other way. It does the opposite. So if I want to evaluate the inverse at 3, well, I would just go the other way. So the domain of the inverse function lives here on this axis. And so I would start with 3 over here, and I would evaluate it by going over to the graph and then down to the x-axis. And we see that the value of the inverse function at 3 is 2. What's the value of the inverse function at 2? Well, I start here, I go over to the graph and then down to the x-axis, and I see the value is 1. What's the value of the inverse function at 1? Well, I start at 1, I hit the graph, and I go down to 0. What's the value of the inverse function at 0? Well, I start at 0, go over to the graph, and I go to the x-axis, but I'm at the x-axis, and I'm at negative 1. So that's how we evaluate the inverse function. We just go from the y-axis to the x-axis instead of the x-axis to the y-axis. All right, so now we know how to evaluate the inverse of a function when we have the graph of a function. But that is not the end of the story. It turns out there are some issues that are going to come up when you start doing this and looking at different examples. Eventually you're going to run into an issue like this. Let me show you a new function. Let's call it the function g. So here we have a graph of y equals g of x. All right, so what goes wrong here? What's the issue? Well, suppose, this is a perfectly normal function. I can evaluate this function at different values of x. If I want to plug in x equals 2, I find that g of 2 is equal to a half. 3, g of 3 is equal to 2. 0, g of 0 is equal to a half. Negative 1, g of negative 1 is equal to 2. Works totally fine. But what about the inverse? If I pick a number over here and then try to find the corresponding x value, what happens? Well, say I pick the number 2. Well, if I go over to the graph of g and then down, as we were doing before to evaluate the inverse, I would find the answer is 3. So it looks like g inverse of 2 is 3. However, I could also have gone to the left and hit the graph and gone down and gotten the answer negative 1. So here's a problem. Is the answer equal to 3 or is it equal to negative 1? Well, this is a problem because we want the inverse to be a function, and a function can only have one value associated to each input. Here we're getting 2 values associated with the input 2, so we're not getting a function. And that is a problem. If this ever happens, we say that the original function, g, is not invertible, or g doesn't have an inverse, or g inverse does not exist. Well, there's something we can do to rectify this situation. If we're willing to adjust our original function g, we can get an inverse. So suppose we did the following. Suppose I just looked at the left-hand side of the parabola that we saw here. So what I've done is I've taken the function g, but I've restricted its domain to only values of x less than 1. Well, now we don't have a problem. If I want to compute g inverse of 2, I only have one graph to go over to, and I come down and I see the answer is negative 1. Right, so everything works fine. I don't have the issue that I had before I could also have looked at the other half of the function, the original function. So if I call this my new function, if I restrict g to values of x greater than 1, again, it works fine. G inverse of 2 is 3. G inverse of 1 is, well, it looks like some number between 2 and 3. It's right here. G inverse of a half is 2. Everything works fine, and so we do have an inverse function. So how do I know when we're going to have a problem? Is there an easy way to identify when the problem is going to occur? Well, let's look at our original problematic function. And if I draw a horizontal line, I see that this horizontal line intersects the graph of our function more than once. It intersects it twice here. Well, that's the problem, because if I take this as the input for my inverse, I'm getting two different answers. And so that's not allowed, and so we see that this is not an invertible function. So this is called the horizontal line test. The horizontal line test says that if there exists a horizontal line that intersects the graph more than once, then the function is not invertible. And so that's what we need to check. Before we compute the inverse of a function, we should always check to see if it passes the horizontal line test. There's a name for functions that pass the horizontal line test. They're called one-to-one functions. And so as a result of what we said, in order for a function to be invertible, to have an inverse, the function must be a one-to-one function. And to test for one-to-one, we just do the horizontal line test. We want to investigate and ensure that a horizontal line does not intersect the graph more than once. All right, well, there's one more thing you'll see when we talk about graphs of functions and their inverses. All right, so let's go back to the invertible function. This one's not invertible because it doesn't pass the horizontal line test, but if we just take that left half, we said that it was invertible. So what we can do is look at the graph of the inverse function here. Now you might be saying, well, we're looking at it, right? The graph is here. I just go the other way. I start on this axis and go to this axis. And yes, you're right. But if we want to graph this as a function of x instead of as a function of y, then what would the graph look like? Well, we can find the expression, the inverse function, as a function of x. And we talked about how to do that in the previous video. All right, and if you do that, this is what you'll get. And its graph looks like this. So here we've graphed it as a function of x. Now, I just want to point out that this makes sense when we look at it. Right? So what is the inverse supposed to be doing? Well, if I take a number 2 and plug it into the inverse function, I should be getting -1 as the answer. That's what this green curve should be doing. When x is 2, you see I go down to the graph and across and I get to -1. It works just right. And it'll work like that for every value. One interesting thing that you'll see here is that these graphs are nicely related. These graphs are symmetric about this diagonal line y equals x. And that is a property of inverse functions. The graph of the inverse function is the reflection of the original function across the line y equals x. Let's just look at another example. Let's look at that other function we had where we looked at the right half of g. Here it is. So we can compute the inverse of this function as a function of x, and you'll get this, and here's its graph. And again, we see that these graphs are reflections of one another across the line y equals x. I can go up here and show you, or we can even zoom out, and you'll see that that's exactly what's happening. One graph is the reflection of the other one across the line y equals x. So that's another way to think about the inverse function. If you reflect the original function across this line, you've got its graph as a function of x.